as I mentioned to you folks previously, I want you to have the opportunity to get on solid foundation with this, because I know it's difficult. But it's important. So, to provide positive encouragement, tomorrow, for the duration of this gathering, you will be tackling an in-class quiz. You'll pick up the copy thereof at the start of class time. We'll let you work till 3:30. So if you're here on time, you got 90 minutes. It'll be one sheet of paper, paralleling, for example, page 1 of exam 1, in terms of length of material and size of the test. Whatever points you accumulate on this will be added to your exam 1 score. I haven't yet established a point value because I'm still working on this project, but it's almost done. But it'll be worth at least 80 points, maybe more. So go get them. I told you, this will focus on the more detailed and challenging aspects of Bronsted-Lowry acid-base chemistry. And I have given you a hint. Can you read this? It says ammonium oxalate. The component ions of ammonium oxalate you will find to be present in our acid-base table. That's the extent of the hint. And I've decided to give you folks the opportunity to tackle this tomorrow, because tomorrow I have to be away in the afternoon for a medical procedure. Procedure will take a couple hours and will detain me for tomorrow, so I'll not be available tomorrow. But I shall be back Wednesday. So with that said, we proceed with chapter 19. Semi-soluble salt equilibria. The most important aspect of such is how, for different salts which aren't very soluble in water, can we, by equilibrium analysis, determine the solubility for the salt. So with that, we remind you at the start of chapter 19, you took a look at determination of the solubility of silver chloride, and then a couple of questions on solubility of silver chromate. Determining solubility for salts like that, very simple. Why? Because neither silver ion, nor chloride ion, nor chromate ion have any Bronsted-Lowry acid-base properties which amount to anything in water solution. Consequence, for such salts, where you don't need to pay attention to any acid-base chemistry, you can calculate correctly the solubility based on the solubility product constant equilibrium alone. But there are not many salts which are semi-soluble and can have their solubilities calculated strictly from KSP. Why not? Because most salts, which aren't very soluble in water, are composed of an anion whose base properties must be considered when you do the solubility calculation. So to illustrate this, we're going to pick on teacher's favorite weapon as an example: calcium carbonate. Now, calcium ion forms a defined hydrate. It's a hexahydrate. And since calcium ion forms a defined hydrate, you might expect this hydrated metal ion to contribute measurably to the acidity of a solution containing calcium ion. But if you go to the laboratory, because you're trying to find out, is this the case? This hydrated calcium ion, as a hydrated metal ion, does its presence in water solution affect pH? In that case, by making the pH come down because our hydrated metal ions are behaving as acids. So what would you do in the laboratory to find out? Well, we talked about this with respect to silver ion. Now with respect to calcium ion, go to the laboratory. Take a water solution containing calcium ion and nitrate ion, or calcium ion and chloride ion. Because nitrate ion and chloride ion are conjugate bases of strong acids. They're weaker bases than water. They're bases, therefore, which don't affect pH in water solution. So if calcium nitrate solution or calcium chloride solution, say 10th molar or 1 molar, where you got the metal ion present at fairly high concentration, if either of those solutions show a pH different from the deionized water you used to make the solution, you will know it's because of the hydrated metal ion. And you would expect, if such was the case, that the pH of the solution, calcium nitrate or calcium chloride, would compare how to the pH of deionized water? Lower or higher for the calcium nitrate solution, calcium chloride solution? Would the calcium ion solution show a pH lower or higher than that of deionized water? If hydrated calcium ion showed an ability to affect pH in water solution? Lower, because the hydrated metal ions are behaving as Bronsted acids. If you do this experiment, you'll find out that the pH of calcium nitrate solution, 10th molar, 1 molar, calcium chloride solution, 10th molar, 1 molar, same pH as deionized water. So we don't need to worry about hydrated calcium ion in water solution as a pH effector. But what about carbonate ion? Well, we've already done some chemistry regarding carbonate ion in Chapter 18. You found out with your work in laboratory. Assignment 3. That water solutions containing carbonate ion are basic and can be quite basic if the carbonate ion molarity is fairly substantial. Like 10th molar carbonate solution for sodium carbonate 10th molar show a pH about 12. Consequently, we're not surprised to see carbonate ion appearing in the base column of our acid-base table. It has a Kb value of 2.1 times 10 to the minus 4. And accounts for why, if we want to calculate the solubility for calcium carbonate or any other semi-soluble carbonate salt, you got to pay attention to this base property of carbonate ion. So it follows that if we want to get S, which represents solubility for calcium carbonate, we're certainly going to look at this equilibrium reaction, because this is the equilibrium reaction established when water is saturated with calcium carbonate. It puts calcium ion in solution and carbonate ion in solution by a process known as dissociation. But the difficulty of the calculation lies in the fact that after this dissociation equilibrium is established, the calcium ion molarity and carbonate ion molarities found at equilibrium are not equal. This concentration is bigger than this concentration, a good deal bigger. Why is this true? Because the calcium ion, when you put it in solution by this dissociation process, the calcium ion just sits there, doesn't engage in any further chemistry. Does carbonate ion just sit there? No. It reacts with water to make bicarb ion and hydroxide ion. How could we verify this is a fact if we are told that the experimentally determined solubility for calcium carbonate at normal lab conditions is 1.4 times 10 to the minus 4 molar, and the solubility product constant for calcium carbonate is 6.2 times 10 to the minus 9. Well, you know from understanding what KSP means, that K for this reaction is KSP calcium carbonate. Which is equal to this concentration product. Molar concentration calcium ion times the molar concentration carbonate ion. So, if this reaction, which exhibits hydrolysis of carbonate ion and the formation of hydroxide ion and bicarbine, if this reaction didn't go anyplace or was inconsequential when we make saturated calcium carbonate solution, if this reaction didn't do anything of consequence, didn't go any place of consequence, how would the molarity of these two ions compare? They'd be the same. And if the molarity of these two ions would be the same, then we could say the solubility of calcium carbonate can be represented as the calcium ion concentration, symbol S, as well as the carbonate ion concentration. And if that were true, S squared would equal the KSP value, and the solubility, the observed solubility, the experimentally determined value would be the square root of KSP. Well, tell me, what is the gee whiz square root of 6.2 times 10 to the minus 9? The gee whiz square root of 6.2 times 10 to the minus 9. What did you say?
8 10 to the minus 4.
I don't like your exponent. Ah, now I like your exponent. Okay? Let's rewrite this as 62 times 10 to the minus 10. And then I'm going to take 64 times 10 to the minus 10, because 64 is pretty daggone close and only a little bit bigger than 62. Because I know the square root of 64 is 8. And the square root of 10 to the minus 10 is 10 to the minus 5. So if it were true that neither calcium ion nor carbonate ion engaged in further chemistry when this equilibrium is established, the solubility for calcium carbonate could be calculated by square root of KSP and would have a value on the order of 8 times 10 to the minus 5. Well, the true value is 1.4 times 10 to the minus 4. How does 1.4 times 10 to the minus 4, size-wise, compare to 8 times 10 to the minus 5? How much larger? Roughly. It's about twice as large. You agree with that? Well, we're finding a solubility then, a true solubility, which is almost double what we would find if carbonate ion didn't hydrolyze, if calcium ion doesn't affect pH. That's true for calcium ion, but it isn't true for carbonate ion. So the upshot from a magnitude standpoint for solubility is to realize, if I am considering the solubility of a salt, which has as a component anion, a base of appreciable strength in water, the true solubility is always going to compare how to the solubility I would calculate strictly from KSP. The true solubility. We're talking about the solubility for a salt, which contains an anion, whose base strength is appreciable in water solution. How does the true solubility of any such salt compare to the solubility that I would calculate for the salt based strictly on its KSP? We just did that. We just, calculated a solubility for calcium carbonate based strictly on its KSP, which means we're not believing any hydrolysis of carbonate ion. We take the square root of this number, and that'd give you the solubility. But we just found out the square root of this number compares how to the true solubility? The solubility true is almost double the solubility based strictly on KSP calculation. So the effect of this hydrolysis, the effect of the reaction of carbonate ion with water, is to make the solubility for the salt a lot greater than what you would expect based strictly on its KSP value. Okay? Now, implicit in this remark, and I want to emphasize this, because students follow this up all the time, you cannot compare reliably the solubility of salts to each other based on KSP values, except in a few cases. So let's forget the except in a few cases. You cannot compare the solubility of salts based on KSP values. You have to calculate solubilities. You have noticed, I should imagine, on our information sheet for quizzes and exams, there's a whole bunch of KSP values listed. And now those KSP values are important to us, because now we're dealing with Chapter 19, where solubility considerations are being made. If you want to compare, if you're asked to compare the solubility of two salts, or two or more salts to each other, you gotta get solubility, not just KSP values. Okay. Now this one we already answered. Okay. And on page 19.6, there's a discussion. The corresponding equilibrium arithmetic is simple, which shows you how to calculate the solubility for calcium carbonate based on an observed pH of about 10.0 for the saturated solution. So let's take a look at this observed pH. Because again, imagine you have a salt. You don't know what it is, but you have found out that it's not very soluble in water. You put a little bit of salt in a lot of water, say a gram of salt in a liter of water, and you shake like hell and all the gram doesn't dissolve. So you know you're dealing with a salt which isn't very soluble in water. But you'd like to know, for this salt, do I have to pay attention to any acid-base chemistry? Or if I am successful in calculating the KSP value for this salt, can I from that value calculate its solubility? What do you need to know about this salt? Well, we've already told you. You need to know if its component ions affect pH in water solution measurably. So I'll ask a question. Anybody remember this system? Put your hand up if you remember this system. We showed you this system on day one of this gathering. This system is water saturated with calcium carbonate. The calcium carbonate was resting at the bottom, so I agitated the system to get the calcium carbonate to be dispersed now through the liquid portion of the system. So that's why the system is now cloudy, because it's a suspension of undissolved calcium carbonate. And this system was treated with phenolphthalein indicator. You should be familiar, at least somewhat, with the behavior of phenolphthalein indicator. Phenolphthalein does not begin to show you an observable red-pink color like this. Call it pink, I guess, is good enough. Until you got a pH that's above 9.0. So with this investigation, phenolphthalein-treated saturated water solution of calcium carbonate, showing us a pink color, we know saturated calcium carbonate solution has got a pH above 9.0. That's what we know. Well, if you then get out the acid-base table, the indicator table that you see on page 1-6 in your 46 lab manual, you'd find out that indicators which can help you determine pH that's above 9.0 would be thymol blue and alizarin yellow R, and there's also indigo carmine. So I'm going to write down some information for thymol blue, shorthand reference HTB. Y at pH 8.0 or lower. G at pH, and blue at pH 10.0 or above. What pH do I write here? Now I'll also tell you, when we looked at yellow and green and blue as developed by an indicator like bromethymol blue, the blue is a very pretty blue. The green is a very green green. The yellow is a distinct sharp gold yellow, or yellow yellow, flower yellow. But this thing shows yellow, green, blue, but the colors are a little bit dingy. Well, let's forget the dingy part. I got some deionized water here and some calcium carbonate. We'll put a good chunk of, if I can get it, calcium carbonate in our deionized water. And here is thymol blue indicator. If this thing stays yellow, I'm going to scream. Ha ha ha. Was originally yellow because at the top we just had some deionized water, and so the indicator met with the deionized water, showed us yellow. But when we saturated the system by the shaking and caused the thymol blue to illustrate the true pH of the system as a function of the system now being saturated with calcium carbonate, we got this blue. Not shiny blue, but it's this distinct blue. So we know with HBTB, the pH now is 10.0 or above. Well, we're at the boundary of this pH change range for this indicator, the upper boundary. So I still don't know if the pH of this saturated system is 10.0 or 10.5 or 11.0 or whatever. So I'm going to go to another indicator. And the name for this indicator is alizarin yellow R. Alizarin yellow R. Alizarin yellow R. I'll call it this. H-A-Y. Hay, so I can put a proton on that thing. And now I'm going to tell you, the color changes that this stuff shows is yellow to yellow-orange, to orange to orange-red. Not really sharp color changes like we saw here, but by eyeball, we can tell a difference between yellow and orange which has got a trace of red color. 10.0 or lower, 12.0 or above. So at a glance, we know pH on the order of 11.0 if we see an orange color. So let's take our remaining cylinder with deionized water. This time I'll put the indicator in first. A good slug of indicator. We can get some, not much color. I want more color. yellow. And the yellow remains. So now we've got the pH determined, at least to one significant figure, for a saturated calcium carbonate solution. The HBT investigation showed pH 10.0 or above. The alizarin yellow R investigation showed pH of 10.0 or below, so it must be 10.0, which satisfies then the colorimetric observations we have made with these two indicators. And as I said, with this data point, on page 19.6, you'll see how you can calculate the solubility of calcium carbonate with an approximate solution pH of 10.0. Now, it is true that the pH for saturated calcium carbonate solution is 9.95. But there's no way we could possibly determine that with this crude method of pH estimation. You'd need a good tuned-up pH meter to find that out. In any case, notice that from this equilibrium reaction, if we have got a hydroxide ion concentration on the order of 1 times 10 to the minus 4, because that corresponds to the pH of 10.0. Then we also have a bicarb concentration on the order of 1 times 10 to the minus 4. So, if we are taking advantage of knowing that the true solubility for calcium carbonate is 1.4 times 10 to the minus 4, then when we made the saturated calcium carbonate solution, which we just did 3 times, well, we did it today 2 times. Establishment of this equilibrium generates a calcium ion molarity of 1.4 times 10 to the minus 4 and an initial carbonate ion molarity of 1.4 times 10 to the minus 4. But the carbonate ion doesn't sit there. It's 1.4 times 10 to the minus 4 minus x, where x is this, and x is this, and x is equal to 1 times 10 to the minus 4. So to what extent has carbonate ion hydrolyzed? To what extent has carbonate ion reacted with water by this process to create bicarb ion? Because clearly bicarb ion is the species derived from carbonate hydrolysis in this system. Well, let's go back to our percent ionization recipe and now apply it to determine percent hydrolysis. You could just as well call it percent ionization, because you see in this carbonate water reaction we're making new ions, so this is also an ionization reaction. 1 times 10 to the minus 4, concentration of derived species, divided by the true solubility, multiplied times 100%, tells us carbonate ion hydrolyzed by this process about 70%. So there's still 30% carbonate in there, but 70% of it went away. And it's going away, so to speak, to make, beside bicarb ion and hydroxide ion, accounts for the observed pH. All right. Now let's see if we are following this chemistry. By asking this question. A different carbonate. We don't know what it is. But let's imagine it's a +2 metal ion carbonate like calcium carbonate. It may not be. But if it's a +2 metal ion like calcium ion, then the formula would be MCO3, where M represents the +2 metal ion. If I make a saturated solution of M carbonate, and I see that M carbonate doesn't dissolve particularly well, it's also a semi-soluble salt like calcium carbonate, and I observe a pH of 11.0, where we got 10.0 for the saturated calcium carbonate solution. So with the indicators we talked about, if I want to get a handle experimentally on this 11.0 value for the pH for saturated M carbonate solution, then I'd have to use my alizarin yellow R, and I should see an orange color rather than this kind of pale yellow. How does the solubility of M carbonate compare to calcium carbonate? If this is the pH for the saturated solution of M carbonate. S M carbonate versus S calcium carbonate. Can we state matter-of-factly from these pH observations for the saturated solutions of each, can we state matter-of-factly that one of these materials is more soluble than the other? With the question being, which one is it? Or is it the case that I need to do more investigations, and I cannot determine which of these salts is more soluble based on this observation? How do you vote? How many vote that I need more investigations? I can't say anything about the relative solubility of these two salts based on this pH observation. Well, nobody's voting for that. Oh, I got a half a vote for that. So, with the exception of a half a vote, you are telling me that you believe you can answer this question. The question being, which of these materials is more soluble? Can I resolve that with this pH observation? The answer is yep, you sure can. All right, which one is more soluble? Is it M carbonate or calcium carbonate, which has a solubility of 1.4 times 10 to the minus 4? Which is more soluble? M carbonate is more soluble. I have a vote. How many support this vote? That's correct. Does it not seem to you that it must be true that when I made the saturated solution of M carbonate, I started with an initial molarity of carbonate ion. An initial molarity of carbonate ion, which compared how to 1.4 times 10 to the minus 4 moles per liter. Which one has the higher initial molarity of carbonate ion? Which one made the higher pH? Which one caused the creation of more hydroxide ion? This stuff did. So I had to have a higher solubility for this stuff because the higher pH is telling me that for this stuff I'm putting more carbonate ion in the solution. You know, if I go to the laboratory and I take 1 molar sodium carbonate, 10th molar sodium carbonate, and 100th molar sodium carbonate, they're all basic solutions. And I know that in the 100th molar sodium carbonate, the carbonate ion hydrolyzed to the largest extent for these three, right? Because that's the most dilute of these three. But the 1 molar sodium carbonate is going to have the highest pH and the highest hydroxide ion concentration because it has the highest initial carbonate molarity. Okay, on we go. Question 19.8. It is an experimental fact that the pH of saturated silver carbonate solution is 10.0. Question. How does the solubility of silver carbonate compare to the solubility of calcium carbonate? Did you say roughly equal? Is it possible they would be exactly equal to 2 sig figs? Is that possible? Yeah, that's possible. Do you agree or disagree? Those of you who have not yet voted. We have just found, about what we did there and what we did here, that saturated calcium carbonate solution to 1 sig fig pH is 10.0. Now we're reporting to you that saturated silver carbonate solution shows the same pH, 10.0. Well then, for each, how must the initial carbonate molarities compare? Got to be the same. So the solubilities have got to be, practically speaking, the same. Now, silver sulfide. We talked a little bit about silver sulfide previously. Do you remember the reaction which you looked at last week in discussion class, and then we talked about on Friday? Silver chloride treated with H2S, resulting in the production of silver sulfide. Also made hydronium ion and put chloride ion in solution. But the main part of that equilibrium reaction was, the most important part of the equilibrium reaction was the observation that silver chloride, which is pretty stable stuff, not very soluble stuff at all, treated with a sulfide source, H2S, readily converts, thermodynamically speaking, to silver sulfide. Conclusion: silver sulfide is a lot more stable and a lot less soluble in water than silver chloride. In fact, saturated water solution of silver sulfide, pH is 7.0. The same as water itself. You're going to make some of this really stable stuff, silver sulfide, when in 46 laboratory you get to assignment 7. From this observation, 7.0 pH for saturated solution of silver sulfide. What can I say about the solubility of silver sulfide compared to the solubility of silver carbonate? Much lower. What can I say about the solubility of silver sulfide in general without comparing it to the solubility of silver carbonate? Can I say fairly that it's awfully damn small? Because I know when I saturate a solution with a sulfide, all the sulfide that goes in solution does what? Yeah, all the sulfide will hydrolyze and convert to hydroxide. Right? We know that about the chemistry of sulfide ion. It is one of our strong bases. And beside hydroxide ion and oxide ion, it's the third of the 3 strong bases we have listed in our acid-base table. So when I see a saturated solution pH of 7.0 for this stuff, which is the same as deionized water itself, provided it's pure deionized water, I know I haven't put much of this stuff in solution. Not at all. So I'll ask another question. Since we're now getting to be experts at acid-base chemistry, I hope. If I wish to calculate the solubility of silver sulfide, clearly I have to look at the KSP equilibrium. And the KSP equilibrium for silver sulfide gives me an immediate handle on pH, does it not? Remember what KSP for silver sulfide looks like? Because when silver sulfide dissociates in water, do you make a water solution which is containing the component ions of silver sulfide? When I make a water solution of silver sulfide, do I make a solution which contains the component ions of silver sulfide at appreciable or measurable concentrations? Now, silver ion's in there, okay, but how about sulfide ion? The sulfide ion converts quantitatively to hydroxide ion and hydrogen sulfide ion by hydrolysis. So I've already got a handle on pH for a saturated silver sulfide solution. And I've got a handle on silver sulfide solubility. Do you think I might need to, however, to resolve the issue of solubility for silver sulfide in water and resolve the issue of true pH for silver sulfide solution? You think I might need to look at another equilibrium reaction? If so, what equilibrium reaction? I'm listening. Warm my ear with the right answer. What is it? We've recognized silver sulfide is composed of an anion which hydrolyzes to an extent of 100%. That's sulfide ion. That gives us a handle on pH. But we want to be able to calculate the solubility of silver sulfide as well as the pH for saturated silver sulfide solution. In this case, the KSP equilibrium accounts not only for dissociation, but also for ionization, because I don't have sulfide ion in the system. I wind up with silver ion and hydroxide ion and hydrogen sulfide ion. Can I, with this reaction alone, calculate the solubility for silver sulfide? Can I, with this reaction alone, calculate the pH for the solution? Saturated silver sulfide solution. Can I or can I? Yes or no? The answer is no. Why not? Do you believe that the solution we are describing is awfully damn dilute? Didn't we just tell you when I dissolve silver sulfide in water, I'm not changing the pH measurably? In fact, if I take it to 2 sig figs, it's still another 0. I'll have to take that to 3 sig figs before I start to get silver sulfide, showing me that the saturated solution is ever so slightly more basic than that of water. So what's this other equilibrium I got to pay attention to deal with the issues that we just talked about? What is it? Very dilute solution. Ionization of water. KW. You betcha. We've reminded you, if you want to understand successfully the chemistry of Chapter 19, what do you have to use as a foundation? Chapter 18. You can't get away from it. Okay. Now, more fun. Look at this equilibrium reaction. A, recognize where this equilibrium reaction comes from. Hint, see what's on that slate. And B, recognize why you have to be careful with this reaction. Because this reaction is not interpretable stoichiometrically. Answer those while I go get my wedge for this board. All right? Where'd this reaction come from? Here's the dissociation reaction for calcium carbonate into its ions. Here's the Bronsted-Lowry acid-base ionization reaction, which accounts for why calcium carbonate saturated solution has a pH above 7.0 due to the hydrolysis of carbonate ion, due to carbonate ion behaving as a Bronsted base. If I take that reaction equation and add it to this reaction equation, what do I get? That one plus this one. Let's call this one I, and this one double I, small Roman 2. If I add up 1 and 2, what do I get? I get that. So that's where this thing comes from. Now, why do I have to be careful with this reaction? Why is it that I can't interpret this reaction stoichiometrically? What does it mean when I say I can't interpret this reaction stoichiometrically?
It means that that isn't necessarily exactly what happens in the reaction.
Be more specific.
You don't have all of the products and reactants properly listed.
Be more specific.
Your ratios for the products?
I don't want to know about ratios. Well, you can talk about ratios. I'll let you talk about ratios if you want to. Let me ask it this way. What's in this system but missing?
Carbonate.
Carbonate ion. Remember? 70% of the carbonate ion went away, but 30% of it's still there. What does that mean? That means if I look at this reaction equation and believe that it tells me as calcium carbonate reacts with water, per mole of calcium ion that goes into solution, per mole of calcium ion that goes into solution, I'll also have a mole of this stuff and a mole of that stuff. Is that true? No. In this system, how will the molarity of calcium ion compare to the molarity of this and the molarity of this? Molarity of calcium ion is bigger than the molarity of this. Molarity of calcium ion is bigger than the molarity of this. Right? Because these things were produced by carbonate hydrolysis, and 30% of the carbonate is still there. 70% of it went away, the carbonate. So that's why I can't interpret this stoichiometrically. Can I interpret the dissociation reaction for any water semi-soluble salt like this one, if the anion component of the salt is a base which measurably affects pH? Can I interpret this stoichiometrically? No, right? The molarity of this will not be the same as the molarity of this. Yet this reaction implies that. And it is true that I can read this reaction equation by saying, per mole of this that dissolves in solution, I put a mole of this as well as a mole of this. That is true. But at equilibrium, the mole of this that I put in solution still is there. But the mole of this that I put in solution still ain't there. Because some of this went away to become bicarbon hydroxide ion. Now, next question. Can I still use this equilibrium reaction to give me a handle on the solubility for calcium carbonate in a water solution buffered at pH 8.00? Could I use this equilibrium reaction to give me a handle on the solubility of calcium carbonate if I didn't know it, but I know that the saturated solution gives me a pH of 10.0? Can I use this equilibrium reaction to get at the solubility of calcium carbonate if I know the concentration of this stuff? The answer is you betcha. Let's see why. We wrote the K expression. Can we evaluate K? Sure. We know how to play that game. I look at my equilibrium reaction, and I let it talk to me. It's like we did with the silver chloride becoming silver sulfide. Just like we'll do with any equilibrium reaction if we have to evaluate its K and we're not given the K. I let this equilibrium reaction tell me that I got to have KSP for calcium carbonate in there. I let this equilibrium reaction tell me that I've got to pay attention to the base character of carbonate ion because I see this reaction really is converting carbonate to bicarb. And that happens when carbonate grabs H+, behaves like a base. So without even doing any calculation, if I think about this reaction, I can recognize it's got to be composed of KSP calcium carbonate and KB carbonate ion. It has to be. Well, to get KSP calcium carbonate in there, I multiply by 1 in this fashion. Calcium ion molarity top and bottom. Oops! Carbonate molarity top and bottom. And then I say calcium ion molarity times carbonate molarity. There's KSP. And then I see carbonate molarity denominator, which means carbonate considered as a reactant, becoming bicarb and hydroxide ion as products. Isn't that this? Sure. That's this. Well, just as we said. This equilibrium reaction is a composite of KSP calcium carbonate and KB carbonate ion. So now I'll put in the numbers. 6.2 times 10 to the minus 9 multiplied by 2.1 times 10 to the minus 4. I don't expect you to remember the numbers. You know how to get them. And if I do that, I should get 1.3 times 10 to the minus 12. Now I'll check my arithmetic. Yep. And go further. To get at the solubility of calcium carbonate in this special solution, buffered at pH 8. Now, before we pursue this, question. How must the solubility of calcium carbonate in this special solution buffered at pH 8? How must the solubility of calcium carbonate in this special solution compared to the solubility of calcium carbonate in straight deionized water? You remember the solubility of calcium carbonate in straight deionized water? pH 10.0? This got pH of 8.0. 8.00. If I now pursue calculation of calcium carbonate solubility in this solution, how will the value I get, if I do the arithmetic correctly, how will it compare to 1.4 times 10 to the minus 4 moles per liter? Is the solubility of calcium carbonate in this solution larger or smaller than 1.4 times 10 to the minus 4, which again is the solubility of calcium carbonate in deionized water, which results in a pH of 10.0. Come on,
Lower.
acid-base chemists. In this solution, write it down. is the solubility of calcium carbonate in this solution, buffered at pH 8, going to be larger than 1.4 times 10 to the minus 4, smaller than 1.4 times 10 to the minus 4, or is it going to be the same value, 1.4 times 10 to the minus 4? I'm curious. I want to know the answer to this question before I do any calculation. In this solution, buffered at pH 8, the true calcium carbonate solubility will be blank than 1.4 times 10 to the minus 4. Greater, smaller, equal to?
Greater.
I got a greater and a smaller. Come on. I want yops from everybody. How many vote greater in this solution? How many vote smaller? How many vote equal to? Who didn't vote? Question. If you wish to kill a base, would you subject it to acid treatment or base treatment? You know this from chapter 18, don't you? If you want to kill a base, you hack at it with an acid. Okay? Now, neither of the systems we are considering are acidic. They both have pHs above 7. But one is more acidic than the other. Which of these systems is more acidic? pH 8, isn't it? How much more acidic is this system than the pH 10 system?
1,000.
How much?
1,000.
How much?
1,000.
How much?
1,000.
How much? 100. Does it not seem reasonable to you that if I have a solution here which is 100 times more acidic than this solution, I'm going to kill carbonate more effectively? And the more effectively I kill carbonate, what do I do to the solubility of this stuff? I make it go
Larger.
up. You want to dissolve this? Murder carbonate ion. Now another dirty question. Did you do that in 45 laboratory assignment 7 with solutions? Did you take some calcium carbonate and treat it with hydronium ion and see bubbles all over, hell and gone? Because you murdered carbonate ion when you hit it with hydronium ion. You turned it into CO2. How many remember doing that? I think one of these days I'm going to teach this course and start out by saying, how many remember this from 45L? You forgot that? You're out. And now let's do the arithmetic. 1.3 times 10 to the minus 12, that's the K value, is equal to the calcium ion concentration times the bicarb concentration times 1.0 times 10 to the minus 6. We got the pH, so we know the hydroxide ion concentration. There's hydroxide ion concentration corresponding to a pH of 8.00. Now, is it fair for me to label the calcium ion concentration as S? Is that fair? Of course. This calcium ion goes in the solution and sits there. So if I wish to determine the calcium carbonate solution, calcium carbonate concentration in any water solution, what I'm really doing is getting the calcium ion concentration, because that is the solubility. Now, what's the bicarb concentration in this solution? Now, if you think about it, you can answer that straight away because we have already recognized that the carbonate hydrolyzed up on the order of 70%. But let's imagine we didn't know that piece of information. So we'll put question mark over bicarb and say to ourselves, I got one equation and two unknowns. I got a problem. And in order to crack this problem, I have to find out how the molarity of this thing compares to S. How does this that's 2 CT S. How can I find that out? We're imagining that at this stage of the game, what we know about this system is its K value and the hydroxide ion concentration because the pH was given. Okay? What do you think we have to consider to resolve this issue in order to know how the bicarb molarity relates to S as F function? What do I put in here? Function of what? Let's put it this way. pH. Now, next question. What are the most possible material forms for this stuff in solution? Possible material forms. I.e., that is, what forms of carbonate are predominant in this system? Well, if bicarb loses H+, it goes back to becoming carbonate. And if bicarb gains H+, it becomes hydrated CO2. So what we're concerned about, to find out how the molarity of bicarb relates to S, is based on pH. What can we say about the relative molarities of the viable forms of carbonate-containing stuff? Because if we can answer that, we'll know how the bicarb molarity compares to S. So, consider the equilibrium reactions which involve the conversion of bicarb to the other viable forms of bicarb. If bicarb behaves as an acid, then I get hydronium ion and carbonate ion. And if bicarb behaves as a base, I get H2CO3, quote unquote, because it's hydrated CO2, and hydroxide ion. So we've already recognized from chapter 18, for the first reaction, K is Ka bicarb. And for the second reaction, K is Kb bicarb. And now I've got the information I need to resolve the issue. So what I'm going to ask you to do, in preparation this time for Wednesday's conversation, is now calc this ratio and this ratio. And if you do these calculations correctly, you'll find out that at pH 8.00, the only form of carbonate ion in this system that amounts to anything is bicarb itself. So for this system, you're going to find out question mark is equal to S. And we'll pick it up from this point next time.